if I get it to, okay, hopefully it's recording now.
Osama,
Yes.
I'm not sure, I don't want to ruin your plans, but do you have a different problem? Because I just did this problem for homework.
Oh,
It's
you did
kind of
this problem
different.
for homework.
Yeah.
Okay. Well, let's see. Did you guys do this problem for homework?
If they have it, I don't mind. I can go through it again. It's totally fine.
I have not, no.
You
I
have
don't
not.
have it.
Okay. Yeah, hopefully that doesn't happen because I don't want to solve homework problems in SI session.
For Armand's class, he has this.
He has this. Okay.
I think he has this problem.
But did you guys at least solve it?
Yeah, I did. I don't know if anyone else has.
I haven't. I was gonna work on the fluids homework after this.
Okay, well, I mean, this problem is a good introduction to fluid mechanics, right? It's hopefully a very simple problem just to get you started with fluid mechanics. But before we jump into this problem, I'd like to ask like a couple questions, see where you guys at right now in fluid mechanics. So in chapter 1, right, we learned about different thermodynamic properties, right, for fluid, right?
Yeah.
Give me a thumbs up. Okay, great. Yeah, we learned about a couple of major ones like temperature, what else? Pressure, density. I think a new term was introduced, which is dynamic viscosity and kinematic viscosity, right? And what else did we learn about? You guys remember? The
pressure, cavitation.
Cavitation. And what about the one major thermodynamic property? It's an extensive one, but I mean it's a very like specific one to fluid mechanics, which is
density,
but in specific, starts with specific. Specific what?
Like specific weight. Like
exactly. Yes, that's the major thing in fluid mechanics is specific weight, right? And it's represented by the Greek letter. You guys
Gamma?
know it? Gamma. Yes. So this is specific weight, and it's basically what? What is it equal to?
Density times volume?
Specific gravity times. Oh wait.
Well, yeah, it's density times gravity, or specific gravity times
the gamma of water, or whatever. So if it's a liquid, then it would be gamma of water. If it's a gas, then it would be gamma of air.
Exactly. Yes, that's pretty good. Yep. And what's the unit? Remember, units are really important in fluid mechanics. They can really mess up your answer. So make sure you're trying to carry on all the units. Like for density times gravity, what's the unit for that one? Or gamma?
For gamma.
Without looking at your notes, try to figure it out yourself. Density is what? Is mass over volume, right? Times gravity. What is that? What's
meters
mass?
per second squared.
What's mass times gravity?
Newton.
Yes, or weight.
Meters.
Just weight. It's measured in newtons, but it's just weight.
Weight over volume. Weight per volume.
Right, over volume, which is meter cubed. Right, so that's the unit for specific weight. That's why we call it specific weight. It's basically weight over volume. That's it. Okay. What else I have? Is this like a good like a brief summary of the chapter? Right. Yeah, we learned about that. Specific gravity. What is specific gravity again? You guys said? SG stands for specific gravity.
It's the density of your like unknown,
Yes.
any liquid divided by, like Derek said, either the density of the water or air.
Or air. So it's density of water if you're dealing with liquids.
Okay.
It's density of air if you're dealing with gases, right? So, and this density at the top is the density of your fluid, right? So density of fluid. And if the specific gravity is equal to 1 and you're dealing with a liquid, what does that mean?
That it's water.
Water.
It's just basically water. You have water right in front of you at 4 degrees Celsius. And if it's more than 1, what does that mean? When you say, oh, the specific gravity of this liquid is more than 1.
It has a greater density than water.
Has a greater density. That's why you're seeing at this example, Sg is equal to 1.6, which is heavier than water. That's why it's at the bottom. Right? If it's 0.9, that means it's less dense than water. So it'll be at the top. Right? So by just looking at this problem, we can see gasoline and liquid with an Sg of 1.6. This means that the liquid is more dense than gasoline. So we're expecting Sg for the gasoline to be less than 1.6, right? Good, bad? Are you guys following?
Yes.
Okay, great. So let's do this example really quick. Any questions? Forgot to ask any questions you guys have, maybe from lecture or anything we talked about, really? No questions? Okay, well, let's solve this example, see how you guys are doing. So I'm not sure, can you read the problem? Is it clear?
I
Yes.
can, but I don't know if other people.
Yes, it's clear.
Okay. Okay, great. So it's asking us to find what is the height, h, of the third liquid. So this is h right here in the right leg, right?
Yes.
Okay, great. So how would you approach this problem? Just don't solve it yet. Just tell me, like, how would you approach it? What's the, we know we're looking for h, but we know the specific gravity of the liquid is 1.6 right here. What else are we forgetting, or are we missing from this problem?
That they share the same pressure, like atmospheric pressure.
Yes, it's open to the atmosphere. You see this symbol right here. It's open to the atmosphere. That means the gauge pressure is what?
0.
Is 0, right? Gauge pressure is 0, but what is the absolute pressure? If it's open to the atmosphere, let's say at sea level. You guys know what's the atmospheric pressure, really? It's like a constant value, almost at sea level. It's a constant value. It's equal to 101.3 kilopascal or 14.7 psi, right? That's the absolute pressure. So let me write down, I think I have the formula, really important. Let's write it down. P absolute is equal to Or, yeah. Yeah, let's write it as P absolute is equal to P. This is atmospheric. You guys have the formula for this, or you don't have it in your notes anywhere?
I think we have a formula similar to it. The pressure gauge formula.
Okay, yeah, let's go with the pressure gauge. So I think PG, pressure gauge, is equal to, can you give me the formula?
Is it P absolute minus PA?
Exactly. P absolute minus PA. And what is a P absolute? PA is what? The atmospheric pressure, right?
Yeah.
Great. Okay. So let's go with this formula. I think it's better. I think the two formulas are the same, really. If you solve for P, this is P gauge. Right? You guys understand this formula? You have two different things. You have absolute pressure and you have gauge pressure. So imagine you're holding a pressure gauge and you're in the atmosphere, right? What's your pressure reading if you're holding a pressure gauge?
It's the difference between like the
The actual pressure and the atmospheric pressure.
yeah.
So
Yeah,
if you're
well,
at sea level, it would be 0.
it would be 0, right? Because it's 0 related to atmospheric pressure. So that's the definition of gauge pressure, right? It's 0 at atmospheric pressure. But what about absolute? What about absolute pressure at sea level? You guys know? What's the absolute pressure?
Minus P.
Solve for this, solve for P absolute, right? I'm asking about what is
So
absolute pressure?
it would be you said 101
101.3
kilopascals.
kilopascals. It will be 101 because if you want to solve for P absolute, it's going to be
PA minus P gauge. Or PA plus, oh yeah, PA plus
Yeah.
P gauge.
it's going to be PA plus P gauge. So the gauge pressure at sea level is 0, right?
Mhm. Yes,
This one is 0. And what is the atmospheric pressure?
101.3.
101.3 kilopascals or 1 atm, 14.7 psi, 760 millimeter mercury. You can measure pressure with a millimeter mercury or inches mercury. That's fine. So you have all these readings, and they basically mean the same thing. So 1 atm is equal to 101.3 kilopascals is equal to 14.7 psi is equal to 760 millimeter mercury is equal to 29.96 inches mercury. So make sure you have this one in your notes. You don't have to keep flipping through the book to look for all these values. They basically mean the same thing, depending on which unit system the problem is using. Some problems will use the metric system, and the other one is going to use the US custom system. Okay, I think that's a good review. What do you guys think? You have any questions? No questions? Okay. Well, let's jump into the problem then.
So for this problem, we have gasoline, and it's not giving us the specific gravity of gasoline. what table would give us the specific weight of gas?
Specific weight, I think. Let me check.
There's table
Oops.
2.1, but it doesn't give specific weight of gas. It gives specific weight of oil.
Of oil. Okay, so check the appendix, right? Make sure you're familiar. I think I found it in the appendix. Table A4, A3, A4. Right, make sure you guys label all these tables, because really, thermodynamics, hopefully you're taking thermodynamics or you already took thermodynamics before this class. Thermodynamics and fluids is basically what? It's all tables, right? If you're really familiar with how to look things up in the tables, you'll do exceptionally well in thermo and fluids. But let's see.
Okay, thank you.
You found, and is it table A3?
Yeah, A3.
A3, okay.
And A4 is for, so A3 is liquids and A4 is gases.
It's gases, okay. And it tells you the temperature in the problem, because remember, does specific weight depend on temperature? Does it or no? What do you guys think?
I think it does.
Well, density does depend on temperature, right?
Yeah.
Yeah.
That means specific weight depends on temperature too.
Yes.
Okay, great. Well, it's in the problem they're giving us 20 Celsius, which is basically normal ambient temperature, nothing special. So you don't have to look special values. It's 20 Celsius is ambient temperature. I think it disconnected. Let me see if I can. Can you guys see my screen?
No.
Okay. Give it 2 seconds. Hopefully you can see my screen now.
Yeah.
Yes.
Okay, great. Let's go back to our problem. So enough with the review. Let's actually do the problem. So they're asking about H. How would you approach this problem?
I would start from one side and go down, find the pressure, and go up the other side.
Yes.
So we know that pressure increases as the deeper you get, and it decreases the higher you go. So when you start from water, it's a positive value, and then get into the liquid, it's a positive value. Then you go up the liquid, so it's minus that pressure from the liquid, and then you go up again, which is minus the pressure due to the gasoline, and it would equal to 0 because the atmospheric pressure from both sides is the same, so they cancel out.
Yeah, you can. That's a good way to approach this problem too. That's good. But let me ask you this. So we know that we're measuring hydrostatic pressure, and what is hydrostatic pressure? Is basically gamma H, specific weight of the fluid times the depth or the height. So if I want to measure pressure or hydrostatic pressure at this point, okay, is the hydrostatic pressure at this point equal to this point right here? Same horizontal line.
Yeah.
Yes.
Yes.
Hydrostatic pressure is equal along a horizontal line, not vertical. It does depend on H, but it doesn't depend on the width or the horizontal line. Right? So if I want to approach this problem, I would say, okay, well, the pressure at this point, right at the bottom, at this point, you guys see it? Is going to be equal to the pressure at this point, right? It's right at the bottom, same horizontal line. So how would we calculate the pressure? First thing, can we calculate the pressure at this point right from the start?
No.
Not really, because we're missing H. We don't know H. But let's go to this point right here. We know they're equal. Let's call this pressure 2 and pressure 1. We know these 2 points are equal, but can we calculate pressure 1?
Yes,
Yes. Why?
because the heights on that's given with water.
Yes, the heights are given, and we know the specific weight for each fluid. Right. So how would you calculate P1?
P1 would be gamma of the water times 1.5 meters plus gamma of the liquid times 1 meter. And we know that gamma of the water is 9790 and gamma of the liquid is 9790 times SG.
Yeah, so gamma of the liquid, this is going to be Sg times gamma of water, right? And Sg is given 1.6 and gamma of water is 9790. That's gamma of water. It's a constant value at 20 degrees Celsius. So make sure you don't have to memorize these values, but it's good to have them like at the back of your head when you're solving problems. Specific weight of water is 9790 Newton per meter cubed. Okay, good.
That the gamma of water, there's no table that gives us those actual values. We have to do that calculation, right?
Table 2.1 on page 64 of the text.
Okay.
Yeah,
No,
but
yeah, go ahead.
oh no, I'm just saying there's some liquids that they give you, and it's on table 2.1,
Mm-hmm.
page 64.
Okay. Thank you.
Yep, so that's basically what fluid mechanics and thermodynamics are. It's just knowing all these values and you know how to look them up. So each chapter will have from 5 to 6 different tables with different values. Make sure you know how to navigate through these tables when solving problems. I just know this value 9790 because I used it like a lot in a lot of problems. Right? I know the density of water is almost 1,000 kilogram per meter cubed, almost 1,000. So yeah, it's just with practice. You can just memorize these values with practice, really. As long as you're practicing more problems, you're gonna memorize these values. Okay, good. That's for pressure 1. And why did we use a plus sign here? Why is it not minus? Right here. Why did we not say, okay, gamma of water times 1.5 minus gamma of liquid times 1?
Pressure increases with depth.
Pressure increases with depth, exactly. As you go down on a vertical line, it's going to increase. Just like if you're diving in the ocean or something, you don't go too deep, right? Or what is going to happen if you go down too deep? I know there are professional divers, they can go too deep and they know how to handle this stuff. But I mean, for a regular person like me who doesn't like to swim, if I go down too deep in the water, I'm going to feel the pressure. And sometimes your bones will crack from the pressure. That's if you go down too deep. I think more than 5 miles or something. I'm not sure. Not sure about the values, but yeah, you can actually crush your bones with this hydrostatic pressure. So if you go down on a vertical line, the hydrostatic pressure increases, right? We're living on the surface of the earth right now. The hydrostatic pressure that we feel is 14.7 psi or 101.3 kilopascals. And what is this hydrostatic pressure coming from? It's basically air. We have this massive, huge volume of air on top of our head that's just pushing us down. right, from the hydrostatic pressure. Okay, good. So what's the value for this one? If you plug in the numbers 9790, 1.5 plus 1.6 times 9790,
30,349.
349. What's the units?
It should be Newton per meter squared.
And that is
Pascal.
Pascal. Exactly. Yes, very good. Following units is really important. That's Pascal or Newton per meter squared. Same thing. Okay, so that's P1. What about P2? If we can do it right here. How would you calculate P2?
It's the same.
Same thing, but it's going to be what?
It'll be with the gasoline. So we have gamma of the gasoline times 2.5 minus H.
2.5 minus H. Okay.
And then it'll be plus the gamma of the liquid times H minus 1. H, I mean, sorry, H.
H, yeah, because the height of the liquid is H. How would you find gamma of the liquid? Gamma of liquid is going to be Sg times gamma of water. Right? You're given Sg is right there, 1.6. Good. And gamma of gasoline, you don't have to calculate anything. It's just a value in a table. You have to know where to find that value. That's it. And why did you say 2.5 minus H though? Is this something given?
Wait, say that again?
Why did you say 2.5 minus H?
Because we don't know the distance from the gasoline to the liquid,
Exactly.
but we know the entire length and we know where H is.
Exactly, yes. The entire distance is 2.5 meters, right? If you sum 1.5, sum up 1.5 and 1, you get 2.5. That's why the length of the gasoline is basically 2.5 minus this height right here. Okay, and what do you do next, though? We know P1, and P1 is equal to P2. So
You can
if
set them equal to each other.
yes, set them equal to each other. P1 is equal to P2. And let me see if I can, oh, next page, nice. P1 is equal to P2. And from there, you can solve the equation for H, right? And what is the value for H?
I got 1.521 meters.
1.521
Yes.
meters.
Did anyone else get that?
Yeah. I
Okay.
did.
Good? Everybody's good with that one?
Yeah. When I solved it though, I didn't know there was a table that gave us the gamma values. So I found the density of the liquid.
Mm-hmm.
I just used like the rho GH in my formula instead of using the gamma times H. I still got the same answer. Just I couldn't find that table.
Yeah, for like I said, for fluid mechanics and thermal, like if you see right here, let me just pull it up. You guys can see this. It's just a binder. I don't know if you can see it. It's just a huge binder I have with all the thermodynamic properties you can think of, right? That's how I solve problems for my classes. That's what I use to prepare myself for the FE exam. is just if you just buy yourself a nice thermodynamic property table, and you should be set, know how to utilize that all these tables, you should be fine. You never have to calculate gammas unless the problem specifically tells you to calculate gamma or something. But you don't have to do any of that if the problem doesn't tell you that.
So what was the gamma gasoline given in the table?
The table, like I said earlier, the table gave oil gamma, but it doesn't give the gamma for gas. So I just found the density, the specific gravity using the densities.
That's a good way, but I'm pretty sure there is a table to find gamma gasoline, right? Somewhere. I think if you check table A3, A4, and if you check table 2.1 or figure 2.1 in chapter 2, I think, go to chapter 2 and start flipping through the pages. I'm pretty sure you're gonna find something for gammas.
Yeah, so 2.1 has it, but it doesn't give it for gasoline. That's what I meant.
Gives
earlier.
it what? Gives it like it has it for water though.
Yeah, it has it for water, oil, ethyl alcohol, seawater, glycerin, carbon tetrachloride, and mercury.
Mm-hmm. But for density, the density of the gasoline, you find it in table
A3.
A3. Okay.
Yeah.
Okay, that's good. Well, if you have the density of gasoline, you can find a specific weight. Remember? Right?
Yeah,
if you
that's
have
what I
density,
did.
Yeah.
just multiply it times gravity, and voila, you have a specific weight. It's just knowing how to manipulate all these equations. That's it, really. Okay, great. Done with this problem. Should I move to a different problem? Good. Okay. Let's see if I can find a different problem. I have a bunch of problems right here. But let's see. Let's do this problem. Can you guys see this one?
Mm-hmm.
Okay. This is a typical problem dealing with manometers. That's what you're gonna see in every exam that has like a manometer problem. It's basically like this one. It can be more complicated, but this one is a pretty good example on how to solve these problems. Okay, good. You guys read the problem?
Yeah.
Okay, great. Yeah, Zoom doesn't tell me who's speaking, so that's why I'm not calling names and stuff. Usually it does when you have your camera on, I think, but it's just it doesn't tell me when you have your camera off, so I apologize for that. One thing I noticed about this problem though is you guys see this one right here, 4 centimeters?
Yes.
This length, I think it should go down all the way to the bottom of the thing. So all the way to here. That's 4 centimeters. Because I tried doing this problem and just it's kind of confusing how they labeled the 4 centimeters. I think it should go down all the way to the bottom to find the pressures. Okay, you want me to go through it, or you guys are solving it on your in your notes or something? Because this is straight from the book. I pull these problems straight from the book.
Yeah, I mean, I'm solving it right now. I don't know if everyone else is doing the same.
But how do you guys want to do this? You guys want to solve it yourselves, or do you just want me to show you how to solve it?
We can come up with a formula together.
Great. Okay. Why don't you guys tell me what to write, and I'll just write it, right? So tell me, how would you find the absolute? So the question is asking to find what is the absolute pressure at point B, which is this point. And what do we know in this problem? We know that SG for this region, region B, is 0.8. So that's less than 1. It's 0.8 at this region. And the absolute pressure at this point A is 1 atm. That basically means it's atmospheric pressure, right? 1 atm. How would you find the absolute pressure at point B?
I would start from the side that I know. So I know the
Okay.
absolute pressure of A, so I would start there.
Okay, you would start at this point. Good, because you know all the heights.
Would it be 1 plus um, the row of water GH? And the H would be 5 centimeters or 0.05 meters.
So you're saying 1 plus,
Row of water,
okay, row of water,
G
G,
times 0.05 meters.
times the height, this one, yes, 5 centimeters. Let's convert everything into meters. That's how I like to do it. Just convert everything to the basic unit meters. So that's 0.05.
Mm-hmm. And then
Okay,
plus, since we're going deeper, so the pressure increases,
yes.
it'd be rho of mercury times G times the height, which is,
Oh, you said row of mercury times G times the height, which is 8.
yeah,
Okay. And what does that give you? What is this formula? It should equal to something.
The pressure at the bottom, right?
Yes, you just calculated the pressure at this point. At the right at the bottom. You moved from point A, which is this point, right here. You moved from point A to this point. Let's call it P2 or P1. Let's call this one P1. Okay, that's how you calculate the pressure at this point. If you plug in all the values, right, density of water, I know that's equal to 1,000 kilograms per meter cubed, or sometimes it's 980. Really, it doesn't really matter if you use 1,000 or 980. But what is the density? You said the density of mercury times G. What is that? How would you find this?
I was thinking looking at the appendix.
One question, why? Why would you look at the appendix?
Because that was the table I was familiar working with.
The problem right here, what is telling you right here?
It's giving you the specific gravity.
Specific gravity for mercury. So how would you find gamma Hg times gravity, or not gamma, density, rho, times gravity? That's equal to what? Gamma Hg?
Yeah.
And what is that? How would you find gamma Hg? Given these SG or specific gravity without looking at tables?
Is it the specific gravity of Mercury times it's something with water, but is it times the density of water, or is it
Gamma of water, right? SG of mercury times gamma of water, right? Because what is SG? Let's refresh our knowledge. SG is density of your liquid. In this case, it's Hg, it's mercury, times density of water, right? But we don't want to deal with densities. We want to convert to gammas, specific weight. What do we have to do? The only thing we have to do in this equation to convert from density to gamma. What do we have to do? We have to multiply the density times gravity, exactly. This formula is equal to, you can add gravity on both the top and the bottom, right? You can multiply the numerator by G and the denominator by G, and you would end up with what? Of gamma Hg over gamma of water. And that's equal to Sg. How would you find gamma Hg? Just multiply Sg times gamma of water, and you'll end up with gamma Hg without looking at tables.
I see. Thank you.
Good. I mean, yeah, definitely you can look at tables, but for this problem, it's giving you SG. Usually when the problem gives you SG, you're safe.
Okay.
Really. SG solves a lot of problems. So when the problem is giving you SG, you're in the safe zone. You don't have to start looking at tables.
Okay.
Okay, so for this one, yeah, you can have this formula in your notes too. I mean, it's basically just Sg, density of liquid over density of water. You can multiply it times gravity to end up with specific weights, because that's what we like in fluid mechanics. We like specific weights more than densities. Okay, so let's take out this one. So that's P1. And how would you calculate PB, or the pressure at point B, the absolute pressure?
You would take P1 that you just found, and then you would subtract the height of the mercury from it, and then also the oil.
Okay, can you tell me what to write down? So you said P1 minus
Minus gamma Hg times 0.04, and then minus gamma of the oil times 0.03.
Exactly. Perfect. Yes. And that's going to be equal to something, which is
PB.
PB.
Pressure of B.
Yes. That's exactly how you find PB. One thing I noticed in this formula, guys, if you look up here in this formula, 1 ATM, we don't really, we're using meters here, right? And we're using density and we're using kilograms. So the standard unit for pressure in the metric system is pascals, right? So 1 ATM is equal to what? Based on the long equation or formula I gave you, what is 1 ATM equal to in pascals?
101.3 kilopascals.
101.3 kilopascals. Are we dealing with kilo in this equation though?
No.
be 101,325 Pascal.
Right?
Uh,
Always use basic units. If you use 101.3 kilopascals in this equation, you'll end up with a wrong value. Why? Because for density, we're using kilogram over meter cubed, and for gravity, we're using what? Meter over second squared? And these units are the basic ones. We're not using any kilos, we're not using anything. So they should match to pascals, not kilopascals. Right?
yeah.
And yes, the basic unit for in a metric system is not gram, it's kilogram for some reason. So you can use kilogram. You can use kilogram, but you'll end up with pascals, not kilopascals. So units, make sure I can't emphasize this really, and it's just units is really important. Fluid mechanics and thermodynamics, really, and knowing how to use tables. Okay, great. We're good on this problem. Can you guys give me a value for PB? We're looking for PB or pressure at point B.
I got a 107,115 Pascals. Does anyone want to check that?
Anyone got a different value? And we said gamma Hg is what? Can someone tell me what's gamma Hg? How did you find gamma Hg in this problem?
SG times gamma W.
Perfect. Yes. And what about gamma of oil? Wow, forgot about that one.
SG of oil times gamma W.
Yes. Times rho W, right? Not gamma W. Or actually it is gamma, right?
Yeah, it should be gamma.
It should be
W.
gamma, yes.
Gamma whatever. Yeah.
Yeah, you're right. It is gamma W, and this is gamma W. Because SG times density will give you what? Like I wrote it before, SG times density of water will give you density of mercury.
Yeah.
But SG times gamma of water will give you gamma of mercury. Right? That's the only difference. Okay, any different values you guys got? Anything?
No.
No? You got 107. So which answer should we pick?
E?
C?
Yeah.
Yeah, pick the closest value. And this happens a lot in the, because this problem, I pulled this problem from the book. It's FE 2.3, so that just means fundamentals of engineering exam. And they always do that. You just pick the closest value. So 107 or 107,000 Pascal is 107 kilopascal, basically. Okay, good on this problem. Are we good with manometers, really?
Yeah.
I think I have a more complicated problem I pulled from the book. 2.31, yes. So this one, maybe for next session. But let me show it to you. It's in the book. Hopefully it's not in your homework though, because I don't want to be solving homework problems. Okay.
I think that is one of our homework problems.
It is? Oh.
Like,
Well, I mean, it's not too bad, right? You just, you're coming here, you're putting in the time to practice more problems, and why not just knock off some homework problems, right? It's not bad. Okay, yeah, this problem, as you can see, it's just it's the same thing. It's a manometer, and it's kind of more complicated with more liquids and the tubes and stuff. But it's basically the same thing. Each problem will be solved the same exact way. You're going from one point to another, from one point to another. And the only thing for these type of questions to remember is the pressure along a horizontal line is what?
the same.
Is the same. Right? It's the same. And does it depend on the liquid though? Right? For this one, we have water. And for this one, we have mercury. So let's say I want to take the pressure at this point and this point.
It's different.
Is it?
It should be because the fluid is different.
Yes. It should be different. Why? Because the liquid, we say the pressure is constant along a horizontal line if you have the same fluid. But for this problem, well, you can ask me, okay, well, is pressure at this point P1 is equal to P2? Because you said the pressure on the horizontal line is equal. Well, no, because now we're dealing with two different liquids. We have water and mercury. But let's say we have mercury right here, right? And we have maybe kerosene, yeah, up there. That's fine. Keep it as kerosene. And is P1 equal to P2 now?
Yes.
Yes. Should be straight answer. Yes. It's the same liquid. It's on the same flat horizontal line. It should be the same. Okay, good. But yeah, let's go back to our problem. So what about this point and this point? Same pressure?
Yes.
Yes.
Yes. And we're probably going to use this this point too to find pressure. Right? What about this point and this point? Same pressure?
Yes.
This point and that point.
Yep.
Yes.
Oh, okay. I thought we were in the water.
Yeah, right at the edge between the two fluid, between kerosene and water, it's going to be the same pressure as this point.
Okay.
Right? Why I'm showing this, why I'm asking all these questions? Because we're probably going to use this concept. You can see we're going to use this point and we're going to say, okay, this point is going to be equal to this point, the pressure. And we're going to calculate the pressure here. And we're going to say, okay, the pressure here is going to be equal to the pressure there. Right? That's how we solve these problems. So we have 2 minutes remaining. I'm just, if you have any questions, you can ask me anything really about the course material, any question you have. It doesn't have to be for this specific problem.
I don't have any questions, but thank you.
Okay, awesome. Thank you for coming. Hope you guys found this
Thank you.
helpful.
Thank
Yeah,
you.
thank you.
Thank you.
Okay, great.
Thank you very much.
Thank you for
Have a good
coming.
rest of your day.
I have a stupid question.
No question is stupid, right?
Might be. You know the problem that we are on before.
Uh-huh.
I was confused how we got the one. It was the second problem.
Second problem. This one.
How the equation was 1 plus. I'm not really sure where that 1 came from. Is that just the formula? Or
Okay, let me
I'm sorry for
let
not
me
asking.
do this. Oh, no, that's fine. And the one was actually kind of misleading. Yes, it's we shouldn't use ATM in our equations, but the student who was helping me out is just P1. How would you calculate the pressure at P1? You
Pressure.
just tell me what to write and I'll write it.
Would it be sure gamma water times 0.05 plus gamma of what is that, mercury times 0.08 equals P1.
Equals P1.
So
Okay.
that would also work to find P1, correct?
Yes, but the
Okay.
question, remember, what is the question asking you? This is if you want to find gauge pressure,
Oh.
right? The question right here is telling you the absolute pressure at point A is 1 atm. And we said, what is 1 atm? 1 atm stands for 1 atmospheric pressure. And what is atmospheric pressure? What's the value of 1 atm?
101.3 kilopascals, but like.
Or we use pascals. We don't like using kilopascals in these problems. So the formula should be like this. You're moving from point A, this one, to P1, right?
Yeah.
Okay, well, you have pressure at point A. Point A, we're using, if it's gauge pressure, it's going to be 0. There is no pressure at point A because you're using gauge pressure. But make sure you follow what the problem is asking. The problem is telling you absolute pressure. So
Okay,
how would you write the formula? You would start with, okay, at point A, we have 1 atm. So it's 101,300 pascals plus gamma water. Hg times 0, and that's going to be equal to P1. So that's the formula, or that's the equation on how to find P1. And what is P1 right here? Is it gauge or absolute?
it's the gauge, correct? Or no?
One more time. It's
absolute.
It's absolute. Why? Why is it absolute?
I'm not sure. Because
we added which term? Which term made this formula absolute? There is one term that made this formula absolute and not gauge.
The first one?
The first one, exactly, yes, this one. These two terms will appear, doesn't matter if you're calculating gauge or absolute pressure, these two terms will stay, will be there. But since we added this term, it made this P1 absolute. We added 1 atmospheric. Now we're calculating atmospheric pressure. If you're including atmospheric pressure in your equation, you're calculating for absolute pressure. If you're excluding this one, take out this one. Now P1 is gauge pressure.
Okay.
Right, but the problem is asking us to find absolute. So why take out this term? Keep it in there. Keep that term in there.
All right. Thank you for explaining that for me.
Okay, great. Hopefully you found that helpful. If you have any more questions, just ask me.
All right. That was the only question I had. Thank you.
Okay, great. Take care.
Same.
Any more questions? Austin? No questions? Okay, well, see you guys on Thursday.